So this is a beam, it's a long beam, and this is the cross section. Right? This shape is the cross section. We want to find the moment of inertia for cross section of this member about x and y axis. X and y axis are given, like these are axes for the composite area, right? X and y. So we are trying to determine the moments of inertia. Let's write for the cross section. Right? So long beam, which is cutting it, and this is a cross section of the member about x and y, and here is the term I was looking for, centroidal axis. Axis passing through the center of an area, or centroid. They call it, refer to it here and there, you will see centroidal axis. All right, let's look at this cross section. It has this weird like this, and then it coming down. Right? Obviously, it's a composite area. We have to divide it into simpler shapes so we can use the information we have in this table to find the area moment of inertia, moment of inertia for this cross section. All right. Now there are a few ways of doing it. There's two ways I can see. You can either go with something like this, one rectangle here. So make it three rectangles. I say this is one rectangle. This is another rectangle. And this can be another rectangle. So three rectangles, you know, each rectangle is basically a simple shape, so you can use the table to find the area moment of inertia about each axis and just add them up. Or the other way, that which is what I did here, we can segment it this way, this one and this one, and say this is one segment, this is another segment, and here is the third segment. Right? This is what I did. Either way, it doesn't matter. It should give you the same answer. It's a little, it might be easier, but a personal opinion might not. You might find the other way easier. As practice, you can always do it the other way and compare the results. Actually, that would be a great practice to play around with this, and also knowing the final answer, you know what the answers should be. So figure out if you did the procedure right. So let's go with this process. All right. So I'm going to do this. Let's do with this cutting. I'm going to cut it here. I'm going to cut it here. Call this segment. Let's call this segment segment A. Call this segment B, and this segment C. All right. Let's start with rectangle B. All right. Now, I have three segments. I have to find the area moment of inertia for, let's say, for x-axis. I have to find the area moment of inertia for x-axis for all these three segments and add them up. And for y-axis, I have to find area moment of inertia or moment of inertia for y-axis for all these three segments and add them up. So let's go with for x axis. Let's do it for x. I'm going to start with rectangle B. Rectangle B. Let's see what we got. I'm trying to find the moment of inertia about axis x and y. If you go to table, not in that direction, this table. X and Y for the rectangle in that segment are basically X prime and Y prime here. Right? Those are the axes passing through the centroid. So area moment of inertia or moment of inertia for that rectangle about X and Y are basically I X prime bar and Y prime bar, I Y prime bar here. Again, we look at the table. What do you have in the table? You know B, the width, you know height, H, and the axes you have for your composite areas are basically the same axes passing through the centroid of the rectangle, which are X prime and Y prime. So I X prime bar and I Y prime bar are going to be your I X and I Y for this rectangle. So I'm doing it for X. So I'll do it separately so we can practice each of them separately. Ix would be, what was that Ix prime? 1 over 12 BH cubed. Right, so 1 over 12 BH cubed. What is B? What is H for rectangle B? I need to know width and I need to know height for this rectangle based on this table. B is this, H is this. So for this rectangle, what is B, what is H? Rectangle B, the one that is separated in the middle.
Base is 600 millimeters and height's 100.
Exactly. Thank you. So that would be 1 over 12, 600 times, sorry, 100.
Bless you.
Thank you. All right, so that becomes Ix for this. Let me see if I have the number. I do have the number. So it's 0.05 times 10 to 9 mm4. And let's just put this Ix for rectangle B. And let's look at rectangle A. I want Ix for rectangle A. Now let's focus on A. Here is A. And here are the axes passing through its centroid. You can call this X prime, Y prime. We want to find Ix. So this is going to be maybe a bit of color. This is going to be dy. As you can see, I need parallel axis theorem because X prime, Y prime, or axis passing through the centroid are not the same axis that I have for my composite area. I know these, right? I know these, but I have to use parallel axis theorem to find the area moment of inertia about a different axis, parallel to this axis, which is X. So Ix would be Ix prime bar plus a dy squared. Right? Ix prime bar is, well, let's go there. Ix prime bar is 1 over 12 bh cubed. 1 over 12 bh cubed. And let me just put the parameters here. Because if I keep using, well, you know what? Let's just keep it as parametric and a dy squared. Now 1 over 12, b for this would be 100. H for this would be 400 minus 100, 300. Plus, the area of that rectangle is 100 by 300. And the distance, dy. Can someone tell me what the distance is? Looking for the orange dy value, the distance between x prime and x. So that would be dy.
250. I mean, 200.
200, yeah, exactly, Tom. It's 300 is rectangle, so half of it 150. Then we have 50 for the distance between the bottom part and the x-axis, which is half the height of segment B. So it's 200 squared. That'll give you Ix for rectangle A as you'll get 1.425 times 10 to 9 mm4. Now let's look at rectangle C. Let's clean this up. Let's focus on rectangle C. Let me keep the segmentation here. And this is rectangle A. Now let's go and look at rectangle C. Here is rectangle C. And here are the axes passing through the center. X prime, Y prime. I'm trying to find Ix. So Ix would be Ix prime bar plus A dy squared. And here is dy, the distance between x prime, x-axis passing through the centroid, and the x-axis for the composite area. Right, everything should be in the same coordinate. So in this case, very similar to rectangle A. Right, you could just write them both together. For rectangle, so we have Ix prime bar, right? If you go back here, it's 1/12 bh cubed, b being the width, h being the height. In this case, width is 100, so 1/12 bh cubed plus a dy squared, 1/12, b is 100, h is again 300, cubed plus the area for this also is similar to rectangle A. So it's 100 times 300. And then the height is 200 squared. From there, you'll get Ix for rectangle C as the same as Ix for rectangle A, right? Everything is the same. So this is 1.425 times 10 to 9 mm4. So we have this, we have this, and we have this. So for the composite area, Ix is basically adding up all these. So for the composite area, Ix is Ix rectangle A plus Ix rectangle B plus Ix rectangle C. You have all of it, right? Just sum them up because there is no cutout here, so just sum them up. If you do that, you should get 2.9 times 10 to 9 mm4. This would be Ix for the composite area.